The Cartesian coordinate system was developed by 17th century mathematician Descartes as a means to graph algebraic functions. It's a way to connect our study of algebra to our study of geometry. Essentially, all it is two number lines perpendicular to each other. Along the horizontal number line, or axis as we call it, is the x-axis, and vertically is the y-axis. And any point along a plane can be delineated by a coordinate pair of x, comma, y. And the origin of the two number lines where they intersect is the point 0, 0 on each number line. Now, you should be aware that each coordinate system is made up of 4 different sectors, 1, 2, 3, and 4 as shown. The upper right quadrant, 1 is positive, positive for x, y coordinates, 2 is negative, positive, 3 is negative, negative for x, y coordinates, and 4 is positive x and negative y. So let's suppose we begin with a point 2, comma 1. That is essentially 2 in the positive direction for x and up 1 in the positive direction for y. Suppose I wanted to plot the point negative 5, negative 4. I would start at my origin, I would go negative 5 on the x-axis, and then I would go down 4 for negative 4 on the y-axis, and the blue point shown in the third quadrant would be negative 5, negative 4. So in that way we can plot any point along two-dimensional space. If I labeled my 2 points shown as A and B, I could even do addition, subtraction, or translation of these points. For example, A plus B would be negative 5, comma negative 4 plus 2, comma 1, the two coordinate pairs of the points A, B. And on the x side, negative 5 plus 2 is negative 3. And for the y coordinate, negative 4 plus 1 is also negative 3. So my resulting point of A plus B would be negative 3, comma negative 3. Let's suppose I had an additional point to plot, 8, comma negative 2. In this case, I would start at my origin and then move in the direction of 8 units to the right along my x-axis. And for negative 2 y coordinate, I'd move down 2 points to plot the point shown in green, 8, comma negative 2. And let's try one more. Negative 5, positive 3. So again, I'd start at the origin, 0, 0. I'd move negative 5 units in the direction along my x-axis and up 3 in the direction along my y-axis. And that would be my new point, negative 5, 3. So in this way, I can plot different points in all different sectors or quadrants along my coordinate system. Let's take a look at a graphed function on the xy coordinate plane. In this case, it's a line. And the equation for this line, as we'll see in later lessons, is y equals x. And we can check the mapping of those points by comparing our equation to different pairs of xy coordinates. For the point where x equals 0, my line goes through y equals 0, so it should run through 0, 0, the origin, and sure enough it does. And when x equals 1, likewise y should equal 1, so my graph of the line should go through the point 1, comma 1. And again, it certainly does. And I could try another point, negative 1 on x, which should translate to negative 1 on y. And yet again, that point is within my line. And I could keep going in that manner. I could go for 4 on x and then check that y is also 4 on my line. And indeed it is. And of course, every point in between the integers as well, which makes up the infinite continuum of my line, in this case, y equals x. Let's start with another function and go about the process of graphing it in the first place by testing out a few points and then connecting the dots. So y equals x squared. Again, when x is 0, 0 squared is 0, so y should be 0 as well. So the graph of this function should go through my origin again, the point 0, 0. And likewise, when x equals 1, 1 squared is 1, so y should also be 1. So far, it looks not too different, potentially, than the line we drew before. But here's where things start getting different. When x equals 2, y will be 2 squared, or 4. And that's a very different point, as shown. And when x equals negative 1, y will be negative 1 squared, or positive 1. And x equals negative 2, y will be negative 2 squared, which again becomes a positive point, positive 4 in the case of negative 2 squared. And we can see our points are looking symmetrical around our y-axis. If we began to connect these points, we would have what we would call a parabola. Which is a curved shape with ever-increasing slope. So in this way, we can actually interpret functions and we can graph functions within our coordinate plane. In both my cases shown, y is some function of x, which is often denoted as y equals f, a function of x. What exactly does that mean, a function? Well, you could think of it as a black box. You'll have an input to the black box, and then it will do its machinations on whatever that input was, and it will produce an output. And that is a function. Now, the unique behavior of a function is that for every one input, that is an x point in this case, there's only one output, a y point. I could have many different x's that translate to the same y output, but what I can't have is one x result in many y outputs. So it's a one-to-one or a many-to-one relationship for a function, but it cannot be a one-to-many relationship. So what does that mean for us graphically? Well, for every x, as we went through before, x is minus 2, I know my output is plus 4 for y equals x squared. For x plus 2, our output of y is x squared, or plus 4. So in this case, we clearly have a one-to-one relationship. Every one x translates to one specific y in our two graphs, that is, our line and our parabola. So how can we test that in general in a graphical manner? A function, whether it is or is not a function. Well, we would look at a vertical line test, as shown in green. So across the range of x's, we can use a vertical line to make sure there's only one intersection for any given x point. And that essentially means there's only one y point for every x input. But what if I had a graph, something like what's shown in brown here? Would that pass my vertical line test? Let's take a quick look. I could plot a vertical line through it, but aha, I see it will intersect at 3 different points, which means there's 3 different y outputs for one given x input. And as a result, this is not a function, or not the graph of a function. It fails our vertical line test. So let's return to our line again. There are a few aspects about a line we want to look into more deeply. They are essentially the slope, the midpoint, and the length of a line segment. So what do we mean by a slope? Generally, we denote slope by the variable m, and that is essentially the rise divided by the run. Or in other words, it's the change in y divided by the change in x. So if I plot 2 points on my line, I could use those 2 points to find my slope. And let's use the points 3, 3, and -2, -2, which both sit along my line y equals x from our last example. The slope is y2 minus y1 divided by x2 minus x1, where I delineate one of my points as x2, y2, and the other one x1 minus 1. Doesn't really matter which one I choose. I could go either way. It'll ultimately work out the same. The key is I want the change or difference between my two y coordinates divided by the difference between my x coordinates. Again, the rise versus the run. So what is that in this case? My y2 coordinate would be 3, and my y1 coordinate would be minus 2. So y2 minus 1 minus y1 is 3 minus 2. And that would be divided by x2 minus x1, which again, x2 is 3, and x1 is negative 2. So my denominator is 3 minus 2 again. And that turns out to be 3 minus 2 is 3 plus 2, or 5, on top and bottom. And the resulting slope is 5 divided by 5, or a slope of positive 1. So what exactly does that mean, positive 1 slope? It means for every 1 unit I move up in y, I move over 1 in the positive direction of x. Let's take another example. Suppose I had a horizontal line as shown in yellow or gold. It intersects the y-axis at y equals negative 5 for every single x. So for each value of x, the y output is negative 5, which means there's no change in y. So y2 minus y1 will actually be 0. It'll be negative 5 minus 5, which is negative 5 plus 5, or 0. And our x2 minus x1 could be anything, depending on the x points we choose. Let's assume we have x2 is 5 and x1 is the origin, or 0. Then my denominator becomes 5 minus 0. That doesn't really matter because 0 divided by anything is 0. So in the case of a horizontal line, your slope will always be 0. What if we had the following line shown in green? This one's a little different. It's downward sloping to the right, whereas our original line, y equals x, was upward sloping to the right. This time it's downward sloping to the right. So what does that mean for our slope? Well, let's take a look. It looks like it's intersecting through point negative 6, 0 on the x-axis, and 0, negative 6 on our y-axis. If we calculate the slope, again, it's going to be the difference in our y-coordinates, y2 minus y1, and the difference in our x-coordinates, x2 minus x1. So as before, it doesn't matter which one we define as x2 and y2 and x1 and y1, but we do have to stay consistent between them. So y2 is 0 minus y1 of negative 6, that's 0 minus 6, or plus 6. And x2 is minus 6 minus x1 of 0 is negative 6. So in this case, I've got plus 6 divided by negative 6, or a slope of negative 1. Aha! That's the difference between sloping downward to the right and sloping upward to the right. Our green line is a negative slope sloping downward to the right. Our original line, y equals x, was upward sloping to the right and a positive slope. So it's essential to recognize from a graph whether your slope will be positive or negative. How about the magnitude of slope? What happens to the graph as our slope goes down and our slope gets higher in number? Well, as the slope becomes less, from positive 1 to, say, plus 1/2, in that case, it means for every 2 we move over on x, we're only moving 1 up in the y direction, whereas before we moved 2 off for the y direction. So a lesser slope, 1/2 versus 1 in this case, means a flatter line. In this case, we're actually moving over 3 on the x for 1 up, so the slope is 1/3. And likewise, I could plot a steeper line, say one where I move only 1 over on x and go up 3 on y. That would be a slope of 3. Remember, our slope is the change in y divided by the change in x, so a change in 3 divided by a change in 1 on the x. And that is a much steeper line, as shown by the blue dashed line. So the steeper line has a larger magnitude of slope, the flatter line has a lesser magnitude of slope, until eventually it gets to 0, at which point you have a horizontal line. What happens if our line starts getting infinitely steep? Our slope is approaching infinity, and then it would go vertical. But what is the slope of a vertical line? As we can see on a vertical line, it intersects the x-axis at one single point. So we can change the y values, but the x value will always be the same. It looks like it's something like -1.25 here. So I can have a change in y, but my change in x will be 0. They're all the same point of x, which means that my slope, I'm actually dividing by 0 in this case, and I can't do that. That's undefined. So the slope of a vertical line is this unique case where it's undefined. And with that, you could probably assess pretty much every line you see. The magnitude of the slope, depending on how steep it is, whether the slope's 0 for a horizontal line or undefined for a vertical line, whether it's positive, sloping upward to the right, or negative, sloping downward to the right. Let's revisit our original y equals x line again. And I'm going to plot the points 3, 3, and -2, -2 once again. And we're going to look at another attribute other than slope of a line. In this case, I want to know the midpoint between my points A and B as shown on that line segment. So what is the midpoint of AB and how do we determine it? Well, it's simply the average of the x coordinates for A and B, comma, and the average of the y coordinates for A and B. So again, I'll label one of the points x2, y2, one of them x1, y1, and mathematically that's x2 plus x1 divided by 2. The sum divided by the count, which there are only 2 points to count in this case. So if we actually plug in the results for this example, my x2 is 3, my x1 is -2, so it's 3 plus -2, or plus 1 over 2. And my y2 is also 3, and my y1 is also -2. So that's 3 plus -2, or 1, divided by 2, again. So my midpoint of the segment AB is 1/2, comma 1/2. And I can even graph that on my line, and sure enough, that does appear to be the point exactly in between point A and point B, my midpoint. And with the dashed lines, we can show it really is kind of the halfway point along the x and the halfway point along the y. Therefore, it's the halfway point along my line. Last but not least, we want to know about the distance between the 2 points A and B on the line segment. How would I go about determining that? Well, in this case, my distance formula is as follows. Distance equals the square root of the difference along the x-axis between the 2 points, that is x2 minus x1 squared, plus the difference in the y-axis points, or the distance along my y-axis, y2 minus y1 quantity squared. And I take the square root of both of those, or that summation, and that will be my distance. So again, let's look at the numerical results for that. In this case, my x2 is 3, my x1 is -2. So the difference or distance between those on the x-axis is 3 minus -2, or 3 plus 2, a distance of 5 squared. On the y-axis, well, my numbers work out the same. y2 is 3, y1 is -2, and that's 3 minus -2, or 3 plus 2 equals 5, and that will be 5 squared. So essentially this boils down to the square root of 5 squared plus 5 squared, which is the square root of 25 plus 25. And I could in turn just call that the square root of 50, or really if I wanted to simplify it, I would think of it as the square root of 2 times 25, which I could break out to the square root of 2 times the square root of 25. And I know the square root of 25 is plus or minus 5 in this case. But minus 5 doesn't have any meaning in the context of our problem because lengths cannot be negative. So the real answer is 5 times the square root of 2. Now the distance formula can look a little messy and be a little harder for students to memorize. So one way I think of it, for those of you who are familiar with the Pythagorean Theorem, and if not, you shortly will be from our lessons, that theorem says my hypotenuse length squared, we'll call that c squared, is the sum of the lengths of the legs, we'll call those a and b, squared. So c squared equals a squared plus b squared. Perhaps you've seen that before. And if I want to solve for my hypotenuse length c, I can then take the square root of both sides. So c equals the square root of a squared plus b squared. And that is essentially our distance formula, where a is the distance along the x-axis, and b is the distance along the y-axis, or the difference between the 2 points. And I'd like to think of it in terms of the Pythagorean theorem because it's easier to remember, and I don't have to worry about the details in the distance formula in the upper left. So let's review what we've done up to this point and look at another example to become more familiar with the process and calculations. We introduced the coordinate system, which is essentially two number lines perpendicular to each other, the x-axis and the y-axis, intersecting at the origin point 0, 0. We looked at the details of what a function is and the concept that a function for every one input, there's one output, and that many different inputs could lead to the same output. It's not possible for one input to lead to many outputs. That would not be a function. We then looked at a line, and we looked at the attributes of slope, midpoint, and distance. So with that, let's take another quick example of it. Suppose I had the points 2, -1, and 5, 4. I'll label 5 for x2, y2, and 2, -1, x1, y1. My slope is going to be the change in y over the change in x, so that's y2 minus y1, and my x2 minus x1 coordinates. So in this case, that's 4 minus 1, or 5, divided by 5 minus 2 for x2 minus x1, or 3. And that gives me a slope of plus 5/3. So this slope should be a little steeper than y equals x that we saw before. How about the midpoint? The midpoint, we said, was the average of the x coordinates and the average of the y coordinates. So it was x1 plus x2 divided by 2 in this case, and y1 plus y2 divided by 2. So if we use our actual 2 points given to try to find the midpoint of those points, that would be in this case 5 plus 2, our x coordinates, divided by 2, and 4 minus 1, our y coordinates, added together, which is 3 over 2. As a result, our midpoint coordinates will be the point 7/2, 3/2. And last, how about distance? Our distance between the points 2, -1 and 5, 4 can be calculated as the square root of the x difference squared plus the y difference squared. And in this case, that's 5 minus 2 for the x difference, which is 3 squared, and 4 minus 1, or 4 plus 1, equals 5 as a distance for the y change. So that in turn becomes the square root of 3 squared plus 5 squared, or the square root of 9 plus 25, which is 34. And the square root of 34 is the distance between the 2 points given.